eagle.
Yeah.
Mm-hmm.
And definitely gives a good definition of eagle eye.
Yes.
There you go.
So before we get to 7:35 here, can one of the VPs listening take minutes? I would say that we should exempt Adrian since he's a co-host. Can one of the other ones do it?
I agree. Where's my right thumb for that? The Eagle says that's a good idea.
Okay.
Joy did contact me earlier, and she's said she's going to try to take notes or do whatever as possible, but she also is going to look at the YouTube video after we get it saved. So
why doesn't somebody just record it?
it is being simulcast over to YouTube Studio, and when we get done there and we turn it off, it will save it out to YouTube. So we are actually recording it.
But I'll still take minutes.
There you are.
Okay.
Thank you, Joy.
She was just concerned whether she's going to miss stuff during the presentation or something. So was that it, Joy? Did I get that right? Okay.
With that, we're up to 38 participants now.
And 5 on YouTube.
We may wind up near 50.
Yeah.
Before it's over, that's half of my most optimistic estimate. So that's good. Think about in a meeting, how many do we usually get? Somewhere between 40 and 50 on a good meeting.
On a good meeting, yeah. I would say average probably 20 to 40, but sometimes we hit 50. Yeah.
So that's a good first virtual meeting for us. Probably a long time coming anyway. We're
because everyone else is just looking at their wall and pretending it's pieces of Atlas.
Yeah.
But the first Atlas, I should say. Apparently, it's the second Atlas now.
It's Comet Holmes, but it did the same thing. Although it was a little bit nicer than Atlas for us.
Yeah.
Yeah, it was still bright when it.
Is it actually going to disappear from here on out? Because I've heard it's breaking up.
It is. In fact, when we did the virtual star party that Doug arranged for us there, that's what he was on most of the time, is just had it on Atlas. It was really neat because you could actually see the movement. In fact, if you watched carefully, you almost could swear you could see it move. But you could clearly see after even a few minutes that it had moved across the star field. You could also definitely see that there were at least 2 pieces to it. A couple times we almost thought we saw 3, but 2 definitely. So yeah, it's breaking up and going away on us, darn it.
That's a bummer.
Yeah. Well, it's like David Levy says, comets are just like cats. They all have tails and they're unpredictable.
Yep.
Okay, I'm showing 7:35.
All right, I think we should officially start.
Yeah.
Go for it.
Okay. Looks like we had somebody's got the microphones muted.
Did I
I
mute
guess
them?
I can.
They're
Looks
working.
like okay, cool. All right. So welcome everybody. You have found your way in through a completely different means tonight to our monthly meeting of the University Lowbrows. Probably everybody here knows that I'm Charlie Nielsen, the president of the club, and I can't seem to get out of it. But I appreciate everybody coming in. We actually are showing now a total of 40 participants, so we're real pleased with that. And so far, anyway, it's going actually quite well. So I did send out the email earlier, so hopefully you realize how we're going to handle this. Basically, I'm going to bring on Mike here in a second. And after his presentation, we're going to ask for any questions to be sent via chat. That way we won't have everybody trying to get on the microphone at the same time. And then it's up to Mike as far as how and when he wants to answer those questions. So, but I guess with that, our speaker tonight is Professor Mike Meyers, who's from right here at the University of Michigan. And the astronomy department. And if you could tell us a little bit about yourself, Mike.
Sure. Thanks, Charlie. And thanks to everyone for showing up at this interesting, unique event. I hope everybody's family and friends are safe and healthy, and as well as can be expected in these extraordinary times. As was said, I'm from UM. I am originally from Missouri, and I did my undergraduate there in St. Louis at the Washington University, and then a master's degree at the University of Missouri, St. Louis, and then went to Massachusetts and did my PhD in Amherst at the UMass there, and then went to Germany and spent a couple of years there as a postdoc at the Max Planck Institute for Astronomy in Heidelberg, and then zipped back the other way and moved to the University of Arizona at the Stewart Observatory. And I was a Hubble Fellow there, and then joined the faculty at the U of A, and I spent 12 glorious years in Tucson, and had a lot of fun. It's a wonderful place. If any of you have probably been there, it's great, clear skies. And then my family and I had an opportunity to go to Europe and take up a position at the Swiss Federal Institute of Science and Technology in Zurich. And we spent 8 years there. And then I'm very grateful that the University of Michigan saw fit to make an opportunity for us to move back here in 2016. So I'm a relatively new Michigander, and been here in Ann Arbor for the past 3.5 years, and we love it and having a great time and doing some fun science, at least for us. So that's where I come from. If you're ready, I can launch into the share.
Absolutely, hit us.
All right, so let me do that. And let me go to presentation mode. There, hopefully
What a
everybody.
nice logo.
Yeah, you can find anything on the internet these days, so there you guys are. And there's the URL in case someone wandered into this meeting and doesn't know where to find this wonderful group of local astronomers here in Southeast Michigan. I'll just acknowledge a few of our collaborators in this work. The folks in blue there are here at UM, and the folks in red are my colleagues at the University of Arizona, with whom I still work on aspects of this project. So some of you will know this picture. This is a reprocessed version of the old pale blue dot picture. You're looking back from out in the solar system, and really through some glints in the camera for the Cassini mission, you can just see a very sharpened and heightened image of the Earth as a dot there, seen against the sunbeam, which is scattered sunlight across the field of view of the camera. And there's a link there if anybody wants to fish that image out. But as astronomers who are starting to study planets around other stars, that work is really motivated by trying to place in context our own solar system, our own planet, and the prospects for life that such planets represent out there in the universe. So I always like to show a pale blue dot picture for context. What we're trying to do, basically, and what I'm going to talk about tonight, are the opportunities we're going to have in the next decade or so to try to take images of planets like the Earth around the very nearest stars to the sun. And ultimately, our goal is to detect those planets and characterize the planetary systems that they're part of, well, ultimately to try to place our own solar system in context. You're seeing here a lineup, like a mugshot or a police lineup of the planets in the solar system. They are shown relative to size appropriate, but of course the orbits are not appropriate. They've all been smashed in very close to the sun just so we can see them, all the relative radii in scale. And we have gas giants in our solar system, Jupiter and Saturn, and ice giants, Uranus and Neptune, and the inner, smaller, denser rocky planets, the terrestrial planets of our solar system, Mercury, Venus, Earth, and Mars. And just to set some ground rules on what is a planet, it's definitely not a grand debate that I want to get into tonight, but there are some interesting scientific questions. It's easy to define a star as something that is big enough that eventually its central temperature will get so high that the relative motions of the hydrogen atoms in the interior can fuse, very rarely, but occasionally fuse enough to drive the energy density in the core of the sun, and stars shine through nuclear fusion. If an object is too small, it will never ever get hot enough to ignite fusion reactions. And so those things are not stars versus stars. And that boundary is about 8%, or 0.076 times the mass of the sun. So things below that that are close to that limit are generally called brown dwarfs, things that are not able to sustain hydrogen fusion in their core and shine. And when such things form, they're warm initially because they have a lot of energy they can extract from the gravitational contraction of those bodies. But eventually they just start cooling and fading over time. And planets do that too. So the boundary between a planet that's Jupiter mass, which is about 0.1% of the sun's mass, or 0.001 times the sun's mass, that's a Jupiter mass planet or a gas giant. And a boundary between brown dwarfs and planets is very fuzzy. People like to make them up. I'm kind of against that on principle. And if somebody wants to talk more about that in question period, I'm happy to focus a bit more on that. Rocky planets, we just differentiate based on their density. And density, remember, is the mass of the planet divided by its volume. And the rocky planets close to the sun have a range of densities, but they're high and they're close to each other. And so the size of an object, given that density, or radius of the object, basically determines its mass. So a planet that's 1 times the radius of the Earth will be about 1 times the mass of the Earth. But a planet that is 2 times the radius of the Earth will be that radius cubed, because the volume goes to the radius cubed, and so it will be 2 cubed, or 8 times the mass of the Earth. And that's a range of planet we call super Earth. So planets around other stars that have masses about less than 8 times the mass of the Earth, we refer to as a collection of terrestrial-like planets, or super Earth planets. Now, I'm sure all 45 people on this call have strong opinions about the difference between planets and dwarf planets, and there are good reasons to have different opinions about that. But again, I don't want to get into that debate myself tonight. All right, so that sort of orients us on the scales of objects we're going to be talking about. Let me go back to motivation. Why do we want to do this? Well, ultimately, I think a lot of the work of folks like myself that study star formation, planet formation, and exoplanet detection and characterization are trying to figure out what the prospects of life in the universe are. However, I should say that is a very long-term goal. And because we don't have a viable theory for the biochemical origins of life, at least even on our planet, I find it a bit speculative to think we would know what a life-bearing planet would look like. And so I think it's a bit dangerous to say we would do experiments to rule out life nearby planets or to detect it with high confidence. I think that's kind of beyond our current understanding. But ultimately, we'd like to get there. We want to explore the neighborhood too. I mean, there are only a handful of stars like the sun within 4 to 6 parsecs. And we can study each of those, and maybe we can find out which one of them have rocky planets and take pictures of them, and ultimately spectra of those planets to find out their composition and characterize them. From my side, I would also like to put theories of planet formation to very hard tests. And a good way to do that is just to put these planets under a microscope, or a telescope in this case, and study them in great detail. And that's something all of us would really like to do. And finally, maybe something possibly even practical. I think when we get a census of hundreds of nearby Earth-like planets and have spectra of those planets, we will find a real bewildering array of diversity of planetary atmospheres. And I think that understanding the range of that diversity and the causes for that diversity in composition and temperature and density, that might help us understand a little bit about the evolutionary history of the atmosphere of our own planet. So maybe we'll even have something practical to tell people in the future. Some of you, I'm sure many of you know your way around the sky better than I do. And this is a picture of many nearby stars. There are even extremely low mass brown dwarfs and white dwarfs that are within the volume of stars represented in this picture that are not shown. It's a little bit of a funny representation, and so I apologize if this is confusing, but it's meant to show a kind of a plane with all those lines that are sort of running from the lower left to the upper right. But that's meant to show the distance from the sun in an axis, and it could be any arbitrary axis. And then another axis is kind of up and down relative to that plane, so you can just sort of orient all the nearby stars to the sun, and the sun is right there at the center. You see Alpha Centauri, the triple system, with Proxima being the closest object to the sun right now, Alpha Cen A and B, Sirius, Vega, many famous stars that you can all pick out in the night sky. And the ones that are shown in with light blue type for the name of the star are ones that have planetary systems inferred around them by hook or crook, by any means necessary. And we're still just getting a very initial census of which of the very closest stars to the sun have planetary systems around them. So these stars that you guys can see in the night sky and know the names of are going to be some of our targets for some of the work that we're going to be doing. I'm not going to talk a lot about planet formation theory. That's a different talk, but we have a kind of a nuts and bolts theory from the late 60s, early 70s, which you can imagine was purely developed to try to explain the coarsest features of our own solar system. And it can do some of that, but I think the one thing everybody would agree on is that planet formation is incredibly complicated. We know that planets are common around stars, but exactly how all of the details work is very much not understood. We have some observations that help us get a handle on some aspects. What you're seeing, and I'm sorry if these funny orange-colored heat map images look weird, but in the center of this image is a star known as TW Hydrae, and the bright versus dark variations that you're seeing are scattered starlight off of dust in a circumstellar disk that is surrounding that star. And we are viewing the system top down. It's almost right in the plane of the sky. And circumstellar dust disks have been seen around many young stars, and this is one of the best examples, one of the closest examples. And there are gaps in between these dust disks, which we believe are due to forming planets that carve out gaps in those gas and dust-rich disks. Exactly what the masses of these planets are, I can't tell you, but you can see at the top, the scale bar is in astronomical units, where the mean distance from the Earth to the sun is 1 AU, and that's kind of a scale here. So these are this is a planetary system going over 100 AU, and the rings and gaps there are at tens of AU, where planets are probably forming in the system and carving up the disk with these gaps. And probably things like this happened in the first few to 10 million years of our solar system's early formation. Well, if we wanted to talk about life, we probably want to spend a moment on something called the habitable zone. I hate that term because, as I said before, I don't think we really understand what is and isn't habitable. But at least even I will agree that there's something we could refer to as the liquid water zone. So if you had a solid body at some distance from a star, I could estimate how much energy I absorb from that star, and then I have energy that I emit from my own equilibrium temperature, and I come into a balance, and I can say what my equilibrium or balance temperature would be. And if that temperature is within the range of liquid water, I could call that the liquid water zone. And I think you could probably imagine stars that are more luminous than the sun would have liquid water zones that are farther away from the sun. And stars that are lower luminosity than the sun should have liquid water zones that are closer to the sun. And hopefully you can see my cursor here on the beam out. There is the Earth at about 1 AU. And as you go up to higher mass stars, those are proportionately higher luminosity. The habitable zone moves out. And if you go down to very, very low mass stars, it gets really close to the star within 0.1 astronomical units. So this is something that folks have talked quite a bit about. Just because you're in the habitable zone doesn't mean you're habitable. And just because you're in the liquid water zone, it also doesn't mean you have liquid water. It depends on how water is delivered to forming planets, how much there is, and how little there is. Turns out that models of planet formation predict too much water. Many tens of Earth oceans worth of water could be a common outcome of the planet formation process as we understand it. So the hard thing maybe isn't to get water, it's to make sure that you don't have too much so that you could have a solid surface for critters to run around on. But again, I digress. What I want to talk about today is how we can try to discover and characterize Earth-like planets around the very nearest stars to the sun. So I'd like to pose this question on this slide to both first-year freshman college students as well as seasoned graduate students who are working on their PhD. Are planetary systems like our own common or rare among sun-like stars in the Milky Way? And I usually make folks take a stand and we do a show of hands. Well, this is a rather ill-posed question. And the answer means, what do you mean by like, I guess? There are many, many aspects to our solar system that are specific. And if I say that 10% of stars like the sun have a planet of 1 Earth radius at the 1 AU, so okay, maybe it's 10%. If I also require that there's a Jupiter at about 5 AU, well, it turns out that only 10% of sun-like stars have that property. If I then require a Neptune at 30 astronomical units, this is getting more specific still. And if I listed 100 different parameters, and each one of them was a 10% probability, and they were uncorrelated, meaning that they all didn't go together, then I would have to multiply 10% times 10% times 10%. And the more I overspecify the properties, the more unlikely it is to get something just like my own. If I really want to know about life in the universe, I would have to figure out first which properties of our solar system are key for the origin of life on the Earth, and then we can have a different kind of conversation. But just to say how common is something just like our solar system, if I specify 100 properties of it, I would say the chances of there being another one with exactly those 100 properties is 0. All right. So let me talk a little bit about how we find planets. Here is a video from the European Southern Observatory, our European colleagues demonstrating the radial velocity method. This is one way we can find planets around other stars, where we watch the motion of the star relative to the planet, or really the common center of motion of the system. And what you're seeing is the planet goes around the star in exaggerated form, but the star in the middle is moving back and forth around the common center of mass of the system. And when the star is moving towards us, all the spectral lines at the bottom are shifting to the blue on the left. And as the star moves away from us, we're looking from the left-hand side over here. And as the star moves towards us over here, the lines get blue shifted. And as the star moves away from us, the lines get red shifted. And by measuring those spectral differences over weeks, months, and years, we can develop a model for the orbit of the system and determine the mass of the planet as well as its orbital separation from the star by using Kepler's laws. And that is a fantastic way to get masses of planets. And indeed, it's how the very first planet around a normal star was discovered. I was just finishing up my PhD thesis at the time when this announcement came and blew everybody's socks off in 1995. This discovery was awarded a portion of the Nobel Prize last year. So we were very, very excited about that. And working in Switzerland and getting to know Michel Mayor and Didier Queloz was a great privilege. Michel, a lovely 70-year-old gentleman astronomer, is a super nice guy, and it couldn't have happened to a nicer guy, I have to say. Another great way to find planets is the transit technique, whereby we don't see a picture like this of a planet moving across the surface of the sun. Of course, some folks on this call have probably observed transits of planets in our own solar system. You can see Mercury and Venus doing this in our solar system. But for other systems, we use the brightness measurement and notice that when the cooler planet is moving across the surface of the sun, the light dips from the star, and we infer the presence of planets, provided we can rule out all the other possible causes of a false positive. So the fraction of this dip that you're seeing in this light curve, so the brightness goes down over time during the occultation, that dip fraction tells us the relative size of the planet to the star's surface. And if we know the star's radius, which we can use other astrophysics to estimate, we can get an estimate of the planet's size. We can also measure the period of this orbit, and that tells us, again, the orbital semi-major axis of the orbit, again, using Kepler's laws. So we get the radius and the orbit, but not the mass from this technique. Here, this big, weird picture of all these circles and all these different colors is a representation smashed all together of the discoveries from the Kepler mission. And when I click on this, let me pause it for a second. When I click on this, what you're going to see are the relative orbital timescales of all these things, and the orbits are drawn out to size, so that planet is farther away. The closer in planets will move quicker, and the farther away the planet is from its star, it'll move slower. The colors of the dots represent the temperatures of the planets. So blue here is cold planets, and the ones that are closer to the center are hotter. And then the relative radii are shown by the size of the dot. So a Jupiter is this big circle, and an Earth is this tiny circle. And here you see the temperature bar from blue to red. I hate that because I know from physics that that's not the way the colors go with temperature, but people think that lava is hot and that should be red, and so that's why they made the color scheme like this. Over on the right-hand side, you'll see our own solar system for scale, and you'll notice that it is very, very different. That's not to say that planets like our own solar system planets are uncommon. It's just that Kepler was super good at finding planets super close to their star, and that's why you see this diversity of these planets here. Kepler has now discovered many, many thousands of planets, and the Kepler mission is over a number of years ago already, and the final data catalogs are out. It was an incredibly successful mission. By far, the biggest bang for the buck, at least in exoplanet surveys. Thousands of planets for a relatively modest cost of hundreds of millions, and just an extraordinary treasure trove of data. And finding these worlds, some of which are even Earth-like radii planets in their liquid water zones. And that's been super exciting to keep mining the Kepler database. Now we get to what I do, which has been less successful to date, which is direct imaging. What you're seeing here is a fabulous discovery of the very first system of gas giant planets around a relatively nearby and relatively bright star. This was an A-type star, HR 8799. And each of these little fuzzy dots out at large orbital radii that you see moving here, these 4, 1, 2, 3, 4, those are gas giant planets with masses between about 5 to 12 times the mass of Jupiter. And again, they have orbits from about 20 all the way out to 70 astronomical units. And all of this stuff you're seeing come and go in the middle, these are artifacts due to the subtraction of the starlight from itself as we try to see faint things near super bright things. And I've even used software to mask out with a hole the super bright A star that would otherwise blast our camera. It's very, very difficult to take pictures like this of planetary systems. But we are now able to do it, and we have about a dozen, maybe 20 systems that we've been able to take pictures of. This one is a beautiful one to show because it has so many years of the orbit. And fortunately, all the planets are orbiting in the same sense, which gives us some confidence that we're actually seeing orbits like from Kepler's laws. And the closer ones are moving faster, and the farther ones are moving slower, just like Kepler predicted hundreds of years ago. So that's the hard stuff, is to find these planets through direct imaging, but we think it gives a lot of great advantages. This is a picture now from several years ago, but showing still a relatively reasonable representation of what we've been able to find so far. I'm showing planets in masses times the Earth. So 1 on this vertical axis is an Earth, 1 Earth mass here. And on the other axis, this way, is shown the distance to the star in astronomical units, or mean distance of Earth to Sun. So 1 times the mean Earth-Sun distance and 1 times the Earth mass, that's the Earth right there. There's Venus, there's Mercury, there's Mars, there's Jupiter, Saturn, Uranus, and Neptune. And all these dots up here are planets that we've discovered around other stars. As we get up to over 1,000 times the mass of Jupiter, I'm not sure I'd even call some of those things planets anymore. Most of these things discovered in orange were from the transit method. These open circles were from the radial velocity method. And a handful of objects that I've numbered here are the ones that I think are reasonable to call directly imaged planets with masses up to 10 times the mass of Jupiter, but no more than that. It's really hard to see things down here at the bottom of the plot. And so the fact that we don't see much down there doesn't mean they're not there. We just haven't gotten so good at detecting them yet. But there's kind of a triangle wedge in this diagram using these various techniques of the kinds of planets. Some, like the ones in our own solar system, there's some real Jupiter analogs out there. We're getting now into the point where we found things that are almost Earth-like analogs, but things like Uranus and Neptune in particular are still very difficult to detect. All right, so I told you I wanted to find Earth-like planets around the very nearest stars. How are we going to go about doing that? Well, the radial velocity technique is really a great and relatively cheap way to find planets. It's been very successful. The challenge is to find things out at a few times the Earth-Sun separation requires long timescales, many years, almost 1 to 2 decades, to see things all the way out to 3 or 4 times an astronomical unit. And so that's ongoing, but it's going to take a very long time before we get out to the distance of Jupiter. Transit, as I hope I've convinced you, has been incredibly successful, and the space missions that are up there are just wonderful. But it's also true that the alignment for transit is very special. You have to have the planet just in the plane between the star and us to block that light, and the probability for that is less than 1%. It's 0.005, or 0.5% of those objects we would see in transit. So the chances are that the nearest planets to the sun will not be transiting. And so we would want a different technique if we wanted to find the very nearest ones. Direct imaging, or taking these pictures of planets, is very complementary to the radial velocity technique because radial velocity gives us the mass. And with direct imaging, we can get an estimate of the brightness of the object. We can get an estimate of the temperature. And from those two, we can make a guess at the radius. And with spectra, we can even get at the composition, what atoms and molecules are in the atmospheres of those planets, and start to, from that kind of astrophysics, tell a lot about the temperatures and densities of the atmospheres, and try to figure out whether there's water in the atmospheres of those planets. So I'm going to go with imaging as a great way to try to find planets around the very nearest stars, but it is super, super, super hard, and so it requires the next generation of instrumentation and the best we can do to make sure that we can see what we need to see. Current radial velocities, so that is this ability to measure these spectral changes in starlight. This red bar I've shown here kind of highlights where we were at about 5 years ago at 1 meter per second clocking speed. So this is literally using the Doppler shift to like a radar gun of a police car. We point our radar gun at the star and we ask how fast it's moving. And 1 meter per second is about human walking speed. It's about how fast you walk down the street. So that's how well we can measure the speed of stars. In order to measure the tiny, tiny movement of a star relative to an Earth planet, we would need to get about 10 times better. And that would bring us down into this regime, 10 times better. We could easily measure Earths. We have a handful of spectrographs that are just able to do that, and more are coming online all the time. So that'll be a great way to find out where these planets are, and maybe even tell our imaging cameras where to point. If you believe me that even though it's unbelievably difficult to take pictures, but it's worth trying, we have to ask ourselves whether we want to do that in light that's reflected from the planets or from the intrinsic thermal emission from the planet. All bodies that have a temperature are emitting radiation due to Planck's radiation law. But most of the images you've seen in your telescopes with your eyes, invisible light, that's all sunlight from the star reflected off of the planets in our solar system. And of course, we can see that reflected light. In this diagram, it shows how bright the sun is relative to the reflected light of 3 planets, Earth, Jupiter, and Uranus in our solar system. And it's down by a factor of about 1 billion. This is in a logarithmic scale. I'm sorry for the complicated math stuff here, but it's a factor of 10 to the 9 or a billion that you would have to suppress the starlight in order to see a planet around a nearby star. And 1 in a billion is tough. If you go out to the 10 micron window, which is about the temperature, the wavelength where the spectrum of our Earth is peaking, because our Earth is about 20 degrees Celsius or about 290 degrees Kelvin. And the thermal physics says that the peak of our emission spectrum should be at about 10 microns, and indeed it is. But the difference between the star up here, the sun, and the Earth's peak is only about 1 part in a million instead of 1 part in a billion. So it turns out to sort of be easier to take pictures of Earth-like planets from their own thermal emission in the mid-infrared or the infrared wave bands compared to doing it in the sunlight in the visible part of the spectrum where it's 1 part in a billion. So 1 part in a billion for reflected light in the visible, 1 part in a million for mid-infrared light in the thermal emission. So we're going to go for thermal emission. And then the next question we would have to ask ourselves is whether we should do that in space or can we try to do it from ground-based telescopes? This is an eye chart you can find on Wikipedia, but I like it because it shows all the telescopes. I don't know, many of them, not all of them I've had the good fortune to use. And it shows how big they are. At Michigan, we love our Magellan telescopes, these twin 6.5 meters at Las Campanas Observatory in Chile. We're partners with Harvard and the University of Arizona and MIT and the Carnegie Institution with those telescopes, and they're terrific. And we love using them down in Chile. The next generation James Webb Space Telescope, which will hopefully be, oh boy, look at that. It was, when this chart was made, it was supposed to be launched in 2018. I've been working on JWST since 1997, so I can't tell you how many launch delays we've lived through in the past 20-some years. But hopefully, it will be launched in 2021. We're going to keep our fingers crossed on that. But it's relatively modest aperture telescope. There are 3 currently planned extremely large telescopes, which I'll come back to and talk about more later. One is called the Giant Magellan Telescope, which is about 25 meters across. Another is called the European Extremely Large Telescope. That is a gargantuan 39 meters across. And the 30-meter telescope is about 30 meters across. There's a basketball field for scale. Tennis, if you're more of a tennis player than a basketball fan. These are big, big glass on the sky. So ground-based telescopes are bigger. And the lowbrows know better than anybody. The bigger the telescope, the more light gathering power. But that's not always the only thing you care about, as you also know. If it's a resolved object, then you're conserving surface brightness, and so the size may not matter to you. If you want finer resolution in scale, and you're operating at the diffraction limit, which requires getting over the blurring effects of the Earth's atmosphere using some fancy techniques like adaptive optics, bigger telescopes give finer spatial resolution when you can beat the seeing limit, which we mostly have to deal with here in Michigan. Correcting for the blurring of the Earth's atmosphere requires this adaptive optics. So what I'm showing here is a little cartoon of how we use bendable mirrors downstream of the telescope, which is shown here. Once we can measure how screwed up the point spread function is, we can correct for it and then get super sharp images with our adaptive optics system. So a bad seeing limited image or speckle limited image shown here, if we can measure the wavefront errors and correct for it, we can zoom down to the diffraction limit. This is something that we do about 1,000 times a second with a very massive matrix inverter with telescopes live at the telescope, and very fancy optics where we have pistons where we can push and pull these mirrors 1,000 times a second to correct for the blurring effects of the Earth's atmosphere to get those fancy, sharp images in the diffraction limit that we really want. But that's not the only thing. Space, it's always clear, so that's fantastic if you want to observe. And it is cold, 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 particularly if you use a sunshade and block out that sun and then passively cool your telescope and instrumentation. Cold is really, really good, especially in the mid-infrared, where a lot of the background radiation from our planet Earth is what bothers us. What I'm showing in this picture is a cartoon of the transmission of the Earth's atmosphere. The rainbow is there showing these wavelengths of the visible part of the spectrum. And then there are these choppy windows in the infrared where we can see through the Earth's atmosphere. And this 10 micron window is a pretty good one. But there are also infrared and millimeter wavelengths where we really have to go above the Earth's atmosphere. And that's also true in the ultraviolet and X-ray part of the spectrum as well. So there are times when we have to go to space. And of course, when you have to, you have to. But then sometimes we can observe from the ground in the infrared. The James Webb Space Telescope, because it will be in space and is a relatively large aperture, will be unbelievable sensitive for infrared stuff, by far better than anything else in the what I call the background limit, where you're limited by the extra light you see in the background. And JWST is just going to be amazing. I can't wait for its launch and the fun stuff we're going to be able to do. However, if you are looking for super faint things near super bright things, you're not always in that thing I call the background limit, where it's the background extra light you're worried about. When I'm looking for planets around nearby stars, the problem is this light from the star itself. And on the left, you're seeing an example. So this is brightness on this up and down axis here. And as I go out in angles farther away from the optical axis, here's what the star looks like. It's bright, and it gets fainter and fainter the far away you go in the diffraction limit. And what we can do is use special fancy optics called coronagraphs to block out that central light from the star. And we can just barely, around the very brightest stars, which will be the nearest ones to our sun, we can just barely get at detecting an Earth with a ground-based telescope that's about 10 meters in diameter. And the future ELTs, it'll be even easier. And we can just barely detect an Earth from the ground. This black horizontal line I'm showing is trying to connect these two graphs. On the left is a simulation of what a next generation telescope fancy coronagraphs will do. And on the right is actual laboratory verified limits on what the James Webb will be able to do. And that's because James Webb was not specifically designed for high contrast, meaning to seeing a very faint things near really bright things. It's better at just looking deep, far away from bright stars, and going deep, 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 looking at the very first galaxies that ever formed. So it may seem strange, but in this special place where we're looking for faint things near bright things, a bigger telescope from the ground that has fancy adaptive optics and fancy coronagraphs will actually do better in being able to see faint things near bright things. And because that is true, in our lab here at U of A, we've been developing a new kind of detector in collaboration with Teledyne Imaging Sensors. We had the good fortune to get the very first one of these in the world. It's a mid-infrared camera, which will have about twice the sensitivity and half the noise of other solid-state imaging detectors that operate at these wavelengths of 10 microns. And we believe this will speed up this observation by a factor of 4 to 8 around the very nearest stars. So imagine you spent $1 billion building a 30-meter telescope, and you wanted to beat everyone in detecting an Earth-like planet around Alpha Centauri, the nearest sun-like star to the sun. We could do it with this detector in a factor of 4 to 8 quicker on a 30-meter telescope. That seems worth investing. The time on one night on these telescopes is about $300,000. And surprisingly enough, that's about how much this detector cost us. So we're very excited about this new technology. We're characterizing it in our lab in this big black can here on the left. And this one is destined for Magellan, which is our Access large 6.5-meter telescope in Chile. And we probably won't be able to get down to imaging Earth-like planets, even around Alpha Centauri. But we'll get close, and we'll learn everything that we need to learn in order to do it with the big guns, which are coming in the next decade. And those big guns are shown here. These are these 3 ELTs. Astronomers love acronyms. It's so confusing. So Extremely Large Telescope has the unimaginative acronym of ELT. And there are 3 projects under development. The GMT, shown in the lower left here, is the smallest of them, but they're hoping to come online first, although they're having funding problems. The upper left one is the European Extremely Large Telescope. And we've had the good fortune to collaborate with a team building a camera for that behemoth. And we're very excited about the fact that we'll be involved in the biggest telescope and that it will get probably built first because it's so far ahead. And we really think we have a good shot at taking that first picture. And then on the right-hand side is the 30-meter telescope that a consortium of U.S. universities are trying to build. And we really hope we can have one of these in the north and one of these in the south. There's some papers that describe some of the technical details of trying to image planets with these giant telescopes. Here's a simulation. So again, the blue is just for effect. It's kind of just showing the noise. And the blacked out part is where the star is. We blacked it out just because it's a mess inside of that big black circle. And on the far right-hand side is a simulation of what a planet around Alpha Centauri A, the nearest sun-like star to our sun, 1.3 parsecs away. If we imaged in this mid-infrared 10 micron window where the bulk of the radiation is coming, you see that planet all the way on the right. That's a simulation of an Earth-like planet with a real Earth spectrum around a star like the sun, just in our backyard. And being able to detect something like that would sure be a thrill. So these are simulations. We have a pretty good understanding of how the cameras and things will work and how big the telescope is. And one of our graduate students here in Ann Arbor, Rory Bowen, is just finishing up a paper which does a simulation of if, everything we know about how common planets are around stars. If we did a survey of the nearest 19 stars, we think there's a really good chance, like 70 or 80% will detect 2 or 3 Earth-like planets around this handful of nearby stars. And many of them we would be able to detect in at least 2 colors. And getting a color would give us a handle or a guess at the temperature of the object. And this would really break things open, that we could start characterizing these things and learning a lot more about them. I'm not paying close attention to the time, but I hope I'm running towards the end and then we can break for questions.
You can take as much time as you need, Mike.
Okay, I'm probably going a bit fast. I'm sorry about that. Hopefully you'll have been able to think of things that confused you and we can go back and review it. But one of the things I'm super excited about with this kind of survey is that while I think doing this in the thermal infrared and looking at the emission, the infrared emission from the planet is definitely the way to go to get that first picture. We can't really know everything about the planet until we get both the reflected light and the thermal emission. And if any of you have gotten really interested in asteroids or other solar system bodies, you know that it's kind of there's something we call the radius albedo ambiguity. In order for me to understand the radius of the body I'm looking at, I also need to know what fraction of the light I'm seeing is reflected versus absorbed by the object. And if I can get the scattered light or the reflected light of the object and the thermal emission, I can break that degeneracy and I can basically do a full-on energy budget. If I know how far away the planet is from its star, I know how much light it's receiving. If I know how much gets reflected back, I know how much it absorbed. And then I know how much from my observations, how much light is being emitted. And if you see that plot there, it's kind of funny. It's got a middle hump. It's kind of got 2 camel humps there. On the left-hand side is the reflected light. And I can even take spectra in reflected light and look for molecules in that reflected spectrum, which would help me understand the atmosphere. And on the right-hand side is the thermal emission, where I can also see absorption lines of those molecules in the thermal emission of the planet itself and put together a whole picture. What I mean by the whole picture is I can actually detect the presence of a greenhouse on a planet around another star. If I knew how hot it was and I knew what energy it was absorbing, I could really look for a greenhouse. And then I could look at these molecules in the spectrum, these absorption dips from water, ozone, CO2, and everything else, and try to figure out where the culprits are, where the villains that are doing that absorbing, that are giving you the greenhouse emission, greenhouse effect on the planetary atmosphere. And that would be super, super exciting. Notice I'm not talking about discovering life. Again, I think that's a bit of a bridge too far. But if I could just detect a greenhouse on a planet around another star, I think that's probably something that we would celebrate and we could retire and have a good time. All right, I think that's my last slide. I just wanted to give you a sense. These new telescopes I'm talking about that can do this thermal imaging will start to come online in 2026 to 2028. So it's kind of a decade from now. I think I've placed pretty many bets. I'm not sure how many beers I'm on the hook for here, but I'm pretty confident that we will have the first detection of an Earth-like planet around one of the very nearest stars within a decade, almost for sure. And if we can combine that with, say, a space-based mission which you might need to do the reflected light part, that will really give us the whole ball of wax, and we'll really be able to understand and characterize these planets. And maybe someday we'll even get to where we had a future mission that could help us look for signatures of life. But I think that's probably beyond my retirement age and maybe even my time on this earth, but we'll see about that. Thank you all very much for your attention, and I'd be really happy to answer questions.
Thank you, Mike. And does everybody see their chat button down at the bottom of the window? And the questions are coming in.
Yes, they are.
Yeah. So we've got virtual applause, and we have a question. I think we'll go in order. The first question is from Chris Inman. Could reflected and emission spectra be used to detect oxygen and O2 on other planets?
That's a great question. And yes, the short answer is yes, but I personally believe it's going to be awfully hard. So I think a couple of the missions that NASA is studying right now could have the possibility of detecting O2 that you see there in that spectrum on the screen in reflected light from a space-borne fancy special coronagraph mission. It's also possible, if you can use the velocity information of the planet moving around the star, that a 39-meter telescope with a very, very high-resolution spectrograph and knowing the orbit and velocity of the planet around the star, you can do what we call a matched filter. In other words, we would know the velocity signature we're looking for, we would know the absorption line pattern of the molecule we're looking for, and we could go for it knowing exactly what we were looking for. And I think there's a chance that that might be doable. The ozone in the mid-infrared, it might be possible to do from the ground, but it is very challenging because we're also looking through the ozone in our own Earth's atmosphere. Again, high-resolution velocity information, where the planet moving around its star would have a different velocity from our planet moving around our sun. We might be able to do a velocity difference detection at high spectral resolution. But absolutely, there are hundreds of my colleagues who think this is not that hard and who are going full out trying to study which biosignatures would be the best. Caution is that it's usually not just one molecule you look for. As some of you will have lived through with things on Mars and even from Viking, you can get fooled. And so you have to be a little careful about false positives. And depending on how extraordinary you think the prospect of finding life elsewhere is, might help you answer how conservative you want to be about making a claim of a detection. On planets, you also have to worry about geochemical processes which can mimic the signatures of life. And so that's what astrobiologists, my colleagues, worry about a lot. But it is in principle possible.
All right. Next question. We have Barry Wiseman, who says, greetings from a fellow Wash U alum. And he's got a couple questions here. We'll go ahead and read them. Are you using HGCDTE IR sensors from Teledyne?
Yes. I'll answer that quickly.
You know what those are.
That's mercad telluride, mercury cadmium telluride. MCT is now what people call them, though when I was a student, we called it mercad tel. And they are the same kind of solid state material that are used in detectors and observatories all around the world. And for JWST, the NASA, ESA, Canadian Space Agency, James Webb Space Telescope, many of the detectors are made out of that material. What's unique about these is that they go all the way out to 15 microns. And while single element detectors of that material, you can change the band gap of the solid state material by adjusting the amount of mercury in the wafer. The new high speed, deep well, high background ones are brand new. And we have the first one, and we're super excited about that. And I can't see the second question on my chat window.
Yep, I've got it here. It's what is the best wavelength range for trying to locate planets by looking for gaps in circumstellar disks?
That's a tougher one to answer because there's a balance between going to shorter wavelengths, which would automatically have higher resolution due to the Rayleigh diffraction limit theorem, but our adaptive optics aren't quite that good at working into the blue, the visible blue. So we're kind of stuck a little bit in a no person's land around 1 micron. The AO works really well, the adaptive optics, to correct for the blurring of the Earth's atmosphere in the near infrared, but you want to go to shorter wavelengths for higher spatial resolution. So right now, the answer to that question is between about 0.8 microns and 1 micron, just redder than the reddest things the human eye can see.
All right. So
and we did have a comment that I wanted to read here from Ani, who said, "Take your time. We don't have to drive back home."
yeah. All right. So let's look at the next question I've got is from Dave. Doesn't direct imaging require the planetary system to be orthogonal to our viewing orientation? And does the angular velocity method require our view to be in the same plane of the planetary system?
The answer to both questions is yeah, sort of. So you're right. In the simulations I showed, we're kind of assuming that we're looking at the system pole on, so that I have the same angle between the planet and the star all the way around its orbit. What we generally assume is a random distribution of inclination. Even if the planet is edge on, we can still see the planet when it is at its largest angular separation, the ANSI, or ANSI, of those elliptical orbits. And then when they move too close to the star, then I get wiped out, both when the planet moves in front of the star and when it moves behind the star. So you're right, it's better to see it pole on because I get more angle in a single view. But what we do with these very nearby stars is note the fact that the orbits are of order 1 year. And for heaven's sakes, I'm going to have to look at a system more than once to actually fully explore the system. So we do simulations for random inclinations and how many times we have to look at it to rule out a presence of a planet if we don't see one. The radial velocity method indeed is optimal when the system is edge on, because that's where the velocities are maximum. But it does work for a range of angles. And for an orientation, a random orientation, the expectation value, if you like statistics, is an angle of about 60 degrees inclination. And that's about half of the velocity signature. So we can correct for some of these effects. But it is true, if the system was viewed pole on and the planet is just moving in a circle around the star, then there's no radial velocity signature, but it's best for direct imaging.
All right. So let's see. Ani has a question. Doug has another comment, but I'll get back to that in a second. Ani has a question. Is it possible for an amateur astrophotographer to detect new planets? And he says, say, with a 2700 millimeter focal length.
There, you can take beautiful pictures of the planets in the solar system. You could possibly even discover new Kuiper belt objects or near-Earth asteroids. You will not be able to image planets around other stars, but what you can do, and I should have made a link to this, is join the worldwide hunt for helping astronomers confirm candidate planets from the TESS mission. I did not mention NASA's new TESS mission that launched last year. TESS is TESS, and Google TESS NASA. It will take you to a series of websites, and you can even join the hunt. There's something called the TESS follow-up program, and people all over the world, amateurs, many hundreds of amateurs all over the world, are doing photometry to help confirm the transit signal or to rule out the presence of transit signals from nearby stars. TESS is, like Kepler, trying to detect these planets through this dipping of the light from the transit method, and that's fantastic, but TESS has very limited spatial resolution. It's a small satellite, and it's about 22 arc seconds per pixel on its detector. So it needs really a lot of follow-up, way more than the professional community can do. And I should type in the chat window if I can pull up a TESS URL. There's a wonderful need for amateur astronomers to help do photometry on bright stars for TESS.
I'll paste that into the live chat on YouTube as well.
Okay, so I'm going to read the next question. Well, I thought I was going to sneeze, but
Actually, Adrian,
I'm
I
not.
think you missed a couple from what I'm seeing here.
Yeah, I'm bouncing back and forth.
Okay,
Doug
gotcha.
has
Go ahead.
another-
Yep.
Yep,
Okay.
Doug's got another one. I wanted to read the one from John's iPad. And then I'll read Doug's again, and we've got Norb Vance on the YouTube. So in that order, John's iPad, are there atom molecules masking surface characteristics of planets?
Yes.
Are three atom molecules masking surface characteristics of planets? I'm not sure if he meant there or three.
Something I neglected to mention is clouds. These planets probably have clouds, and that can complicate our search for atmospheric characterization. Yes, it's certainly true that many of the planets we will detect will have such thick atmospheres, like Venus, we will never see to the surface of the planet. So we will try to characterize whatever we can. There are dreamers who hope that if we got good enough data, we could maybe monitor an Earth-like planet over its orbit, maybe even detect a rotational period. You know, if you had an infinite telescope and you were living on Epsilon Eridani and looking back at us, you might get to see a signal of the rotation rate of the Earth. You might start to see a little modulation due to clouds on the planet of the Earth and see that. You might even see seasonal variations. But for any facility that we are planning, I think that is really beyond the pale. We probably won't be able to do that. But it's true that we will often get stuck with the thickness of the atmosphere. We won't be able to see to the surface, like on Venus, and we'll have to infer the properties of the planet from the upper altitudes of the atmosphere.
All right, so Doug came back with a question/statement. He says, I assume the liquid water zone is based on Earth's atmospheric pressure and composition. How would different gases or gas fractions affect the LW zone distance or extent?
It's a great point, and it's one that I make often. Other colleagues, a friend of ours, Sarah Seeger at MIT, many years ago now, 8 or 10 years ago, wrote a paper about how you could have a liquid water planet way out at 10 astronomical units if it had a thick enough molecular hydrogen atmosphere. Now, for various reasons, that might not be an interesting place to live, but this idea of liquid water, the answer is we don't know, again, because there could be such complexity in the atmospheres of these planets. The liquid water zone could be an awful lot wider than we think. You probably are also familiar with water, at least for short periods, being spewed out of geysers of the satellites of the gas giants in our solar system. And there's probably a thick liquid water ocean underneath the icy surface of Europa. So there are lots of ways there could be liquid water at all different orbital separations of the solar system. And I think we should be cautious about over-interpreting the details of any one system.
All right, so the next question will be Norbert Vance and then Doug Knoll. I'll get yours. Norbert says he wants to know your take on the new satellite constellations and their effect on research.
Oh boy. I am a member of the Dark Sky Association, which I assume many of you are, and there's been some wonderful work. My colleague Sally Uwe has been at least gotten the attention of the university. And so we've all been working hard to keep our skies dark. And I defer to my colleague, Pat Seitzer, who's been doing quite a bit of work on this. Some of you probably know Pat. He's been traveling around and trying to make people wary. While many people support the idea of cheap and available internet, in particular in this time of global pandemic, when we all need it, there is certainly a balance to be struck. And I guess there are concerns, and Pat has articulated them, particularly to our leaders in Washington, D.C. And I hope that something sensible can be done. I guess what I would hate to see happen is for it to be a Wild West, where different companies were competing with each other to get better coverage and faster speed, and all of a sudden we'd have a real problem on our hands. It's wonderful that companies can actually launch things into space safely, reliably, and relatively cheaply, and our space program is going to benefit from that. But I hope there can at least be some regulation and some balance and some consideration for keeping the skies dark. But I'm not an expert, and I'd have to defer to my colleague Pat Seitzer on this one.
Yeah. So Doug Knowles asks the question: would the spectral resolution be fine enough to get rotation rates of planets?
In principle, yes. And for gas giant planets, this has already started. Marta Bryan, a young astronomer at the University of California, Berkeley, has been able to measure the rotation speeds of several gas giant planets. And many of them are at least in the range of the gas giants in our solar system. So that's quite interesting. Ultimately, it might be more from the light curves and the coming and going of clouds in the photometric signal that might make it easier to detect rotation speeds than in the velocity signatures in the planets. But I also have to give a shout out here to my colleague at UM, Emily Rauscher, who does 3-dimensional hydrodynamic simulations of planet atmospheres. Right now, she's focused on hot Jupiters because that's what we can see observationally. But in the future, for her PhD 10 or 12 years ago, she took a global climate simulator for the Earth and adapted that to exoplanets. And her and her colleagues have found all kinds of fascinating dynamical effects in rotating planets where you can see them in the data, but you have to know what you're looking for. So yeah, I think there is great opportunities in the future for that level of characterization.
All right, so we're going to try a direct question. John Maney rose his hand. I saw that. So, John, I am unmuting you for this question. Unmute audio. All right, John, go ahead.
Yeah, I just wanted to say thank you for a very well presented talk. I'm glad to be participating again from Illinois.
Yeah, John, it's good to hear from you again.
Thank you. You're very kind. I hope you're a Cardinals fan, though, John. I mean, I can't really get involved with any Cubs, White Sox stuff here.
I still have a place in my heart for the Tigers.
Okay, I'll accept that.
It'll take a while to change that.
All right. So, anyone else via chat or by raising your hand if you have any other questions for Mike Meyer?
Looks like Mr. Archbold. I saw a hand wave there.
All right, let me find him.
Just wanted to.
Yeah, just unmute. Go ahead.
Just wanted to say it was great to be able to join all you gentlemen this evening from New Mexico. Okay. Sorry you don't have our wonderful clear skies, but you've got a lot of other great things going for you in Michigan. Thank you.
I'm looking for your mute button here. No, I'm just kidding. Thank you for letting us know. We really appreciate that. That's part of the benefit of this technology. So, no, we appreciate that. Anyone else? I think this might be Charlie. Might be a good time to make a final call here.
Yeah. Last question.
Yeah, I'm gonna have to go in a minute and get my kids to bed anyway. So.
Got it.
Okay.
So real quick then, in conclusion, and while Mike is still with us, I just wanted to say that usually about now I would present our speaker with a club t-shirt or a nice lovely club cap in this case. And what was really cool is Mike said that he thought it would really be neat if he had the cap and he was going to give it to his son. And then he came right back about seconds later and said, hey, I'll make you a deal. If you could send me a second one so I can give to my daughter, I will in turn make sure they both become future lowbrows, and I give you an IOU for a future call. That was one of the easiest deals I ever made. So thank you, Mike. And yes, we will get you back. It'll have to be sometime next year, but we'll be in contact with you about that. So
no problem.
And thanks again.
All right.
We really appreciate it.
I tried unmuting everyone just so that we might be able to have him hear a virtual clap.
There you go.
And you're all all very
Excellent
kind.
talk.
And I have to say, I think the University of Michigan Astronomy Department is very, very grateful for all of the wonderful outreach and educational work that you all do, all across the state and probably all across the country. We are very grateful and thankful that you guys exist, and I think it's a great partnership. So let us know what we can do to help.
Go Redbirds!
Guess we'll have to wait till
Hey, Doug.
So do any of the officers have anything that they really need to report?
I'm going to report on behalf of GLAC that although there have been a lot of cancellations lately, with our event being in September, we're not going to cancel as yet, but we're going to pay attention to the events as they unfold all over the world, and with how the COVID-19 spread is, and we'll be continuing to review it. There may be some online options that we'll consider if it does come down to it, and in lieu of having everyone meet, we'll still try and do something on those days. So that's kind of my input, kind of from a GLAC side.
Thank you, Adrian. Anybody else? Okay. In that case, I do have the gavel. Do we have a motion to adjourn?
So moved.
Okay. Thanks, and we'll see if we can do this again next month, because we probably won't be able to meet live, but we'll just have to see how it goes. So thank you, everybody. This has actually been rather fun, and it looks like it was pretty successful.
Yep.
Have a good rest of the evening.
Thank you all. Take care and be safe, everyone.
Yes.
You too, Michael. Thank you for
Bye-bye.
Thanks.
Drive home carefully.
Well, in about 30 minutes or so, the YouTube video should be available for download or whatever. It usually takes about that long for it to save, so it will be online, and all of your wonderful comments and questions.
Doug, Nell, did I see you drinking online?
No.
Oh, that's what I thought, yeah. We got a virtual breathalyzer, you know. Take
Who's
care,
driving?
All right. Bye.
I'd just like to say thank you for the opportunity to come to a meeting, because we're in Northeastern Ohio and we've only been to, I think, one meeting. We see you often at star parties, but that's not going to happen this year. So we've been members for a while, but we never get to come to meetings. So this is kind of fun to be able to do this and put names and faces together.
It was very nice to see you join.
Yeah, well, Jeff and I and the officers will do a little talking amongst ourselves when things return to normal about the feasibility of still having this capability, even when everyone else is going to be in the room. So it's something we're going to look into.
That would be nice. That would be nice.
And the eagle over here says it might be a good idea.
Okay, we're signing off. Thanks, everybody.
Thank you.